just about everything, including Bitcoin Cash people, BTC people. It's kind of all over the place. And even people in BSV, I'm sure, probably don't fully understand a lot of these concepts. And if you've been watching every one of our videos, listening to our podcast, whatever, you might already know some of this stuff. But it's always good to rehear it and rethink about it. So I encourage you to do that as well. So we're going to start off just off the bat. I'm going to assume that you have some kind of a working knowledge that Bitcoin is a currency, an electronic currency. I'm going to just jump in, and we're going to go from very beginning to very end as our understanding of Bitcoin has evolved. So Bitcoin is a peer-to-peer electronic cash system. It is not a digital gold system. In the title of the white paper right there, it's Bitcoin, a peer-to-peer electronic cash system. And in the abstract, it clearly defines actually what this paper is novelly doing, or the novelty, I guess, that this paper introduces, which is that we propose a solution to the double spending problem. So I'll back up. Digital signatures, I'll just read this whole abstract. A purely peer-to-peer version of electronic cash would allow online payments to be sent directly from one party to another without going through a financial institution. Digital signatures provide part of the solution, but the main benefits are lost if a trusted third party is still required to prevent double spending. We propose a solution to the double spending problem using a peer-to-peer network. Now, I'm going to stop right there because this is the first fallacy of Bitcoin, is that Bitcoin introduced blockchain to the world. So there's a lot of, again, very intelligent people that have fallen into this trap of thinking that blockchain is something new. And it's actually not. And so for the low price of $9.99, I can prove it to you. So you can come to Amazon, and I will put a link, and buy this book right here. It's a very small book called Policing Online Games, and it's written by Peter Weiner. Okay. This book right here actually describes how to create a digital currency inside of a game using a chain of digital signatures. Okay. So someone actually described how to build a currency inside of a game that used a chain of digital signatures. So this is really important because this book was written in 2005. So actually, the blockchain is not the new concept of Bitcoin. The new concept is that we propose a solution to the double spending problem. And previously, the solution required a trusted third party. So what is the solution? The solution, of course, is a competitive proof of work system. So I'll read the rest of this abstract just for anyone who hasn't read it. The network timestamps transactions by hashing them into a block, hashing them into an ongoing chain of hash-based proof of work, forming a record that cannot be changed without redoing the proof of work. The longest chain not only serves as proof of the sequence of events witnessed, but proof that it came from the largest pool of CPU power. As long as a majority of CPU power is controlled by nodes that are not cooperating to attack the network, they'll generate the longest chain and outpace attackers. The network itself requires minimal structure. Messages are broadcast on a best effort basis, and nodes can leave and rejoin the network at will, accepting the longest proof of work chain as proof of what happened while they were gone. So what we're going to kind of get into here is very briefly, what is this system, this solution that Satoshi Nakamoto proposed? What he's actually describing here is a competitive system of nodes in the network competing to find the next hash-based proof of work and broadcasting that out to the network. Okay, so this is, of course, finding the block that everyone hears about when they hear blockchain. So we're going to jump down here real quick because this is something very important. So there's a section about proof of work. It basically, so proof of work involves scanning for a value that when hashed, such as with SHA-256, the hash begins with a number of 0 bits. The average work required is exponential in the number of 0 bits required and can be verified by executing a single hash. So there's more stuff here. Obviously, everyone should be reading this paper, but we're going to jump down a little bit further. The proof of work also solves the problem of determining representation in majority decision making. If the majority were based on one IP address, one vote, it could be subverted by anyone able to allocate many IPs. Proof of work is essentially one CPU, one vote. The majority decision is represented by the longest chain, which has the greatest proof of work effort invested in it. Now, this is really important because the current paradigm in the BTC network, which is, as you'll find, not Bitcoin, because everything I'm going to describe today describes only one Bitcoin that exists today, is that you can run a node and contribute to the network. If you actually read Mastering Bitcoin by Andreas Antonopoulos, if you read a number of other resources that were put out to help you understand what allegedly Bitcoin is, it describes a mesh network system where spinning up a node and connecting to the network implies that you are a part of the network. This is the thesis of SegWit and the user-activated soft fork. So I'm not going to get all into that because I'm going to assume you have some working knowledge of Bitcoin's history. But basically, what that is the idea that you can run a node, that you have to run a node to validate transactions, and that nodes that are not participating in proof of work have any say on the rules. Now, this is flawed completely because we can see here in step 5 of the white paper, section 5, that the steps to run the network are as follows. And to run the network means to be a node in the network. Number 1, new transactions are broadcast to all nodes. This has become important later on. Each node collects new transactions into a block. Okay, so nodes are actually working to create blocks. Each node works on finding a difficult proof of work for its block. When a node finds a proof of work, it broadcasts the block to all nodes. Nodes accept the block only if all transactions in it are valid and not already spent. Nodes express their acceptance of the block by working on creating the next block in the chain, using the hash of the accepted block as the previous hash. So you can see here, actually, for people that have bothered to read the white paper, running the network, being a node in the network, means only being a miner in the network. Okay. Again, not news for a lot of people, but very important to understand if you aren't trapped in the BTC cult. So there's a lot more here that we wanted to talk about. Obviously, incentive is a big piece, but we're gonna get back to that later. So we've kind of already tackled. Okay, so in order to run a node in the network, you have to be a miner. Now, why is this important? Because Bitcoin is what's called a Stackelberg competition. Okay, so I'll kind of read a few things here just from Wikipedia, but there's a lot you can read about this on the internet. The Stackelberg leadership model is a strategic game in economics in which the leader firm moves first and then the follower firms move sequentially. It is named after a German economist who published Market Structure and Equilibrium in 1934, which described the model. Now, in game theory terms, the players of this game are a leader and a follower, and they compete on quantity. The Stackelberg leader is sometimes referred to as the market leader. There's a few more important things here, but before I go on, it says, in game theory terms, the players of this game are a leader and a follower, and they compete on quantity. In Bitcoin, quantity is hash rate. So I should have this up, I guess, but I'll pull it up real quick. So you can see in Bitcoin, there's a lot of different... here we go. So in Bitcoin, you can see that there are competitors. So these are all different miners, mining pools. And you can see here that basically all these different actors can be seen as players in the Stackelberg game. And in our case, CoinGeek would be the Stackelberg leader. And they're all competing on this quantity of hash rate. Okay. So this is really important because basically this prevents any kind of monopoly from occurring. So this is a game theory topic, and this really ties into economics itself. But in order to not convince you that economics is that free market economics is what we're talking about here, which it really is. Basically, we can just assume now that monopolies are almost impossible as long as people are competing for quantity, which of course they are because they want to make the most amount of money. Bitcoin can never be controlled by just one entity. So we're going to come back to all this because this is all important when we lay out the network structure. But I want to talk about something real quick. So if we go through here, there's actually no there's nothing in the paper here that says that Bitcoin is a unscalable system. There's nothing really about scale whatsoever. Now, there's a few things we can talk about, but I want to just bring up a quote from Satoshi Nakamoto written in 2009, April 12th, 2009. Satoshi Nakamoto writes, the existing Visa credit card network processes about 15 million internet purchases per day worldwide. Bitcoin can already scale much larger than that with existing hardware for a fraction of the cost. It never really hits a scale ceiling. If you're interested, I can go over the ways it would cope with extreme size. Now, unfortunately, Mike Hearn never pushes him to go over more ways. I wish that we had that for all the people that are out there that don't think it can scale. But he then goes on to keep saying, by Moore's law, we can expect hardware speed to be 10 times faster in 5 years and 100 times faster in 10. Even if Bitcoin grows at crazy adoption rates, I think computer speeds will stay ahead of the number of transactions. So, of course, Bitcoin has not grown at crazy adoption rates in the past years. There's a few more things that I want to touch on before we even go in. He does talk about fees here. That's important, but not as important. But I'm going to go over these two things here. Eventually, most nodes may be run by specialists with multiple GPU cards. For now, it's nice that anyone with a PC can play without worrying about what video card they have, and hopefully it'll stay that way for a while. Blah, 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 blah. A key aspect of Bitcoin is that the security of the network grows as the size of the network and the amount of value that needs to be protected grows. The downside is that it's vulnerable at the beginning when it's small, although the value that could be stolen should always be smaller than the amount of effort required to steal it. If someone has other motives to prove a point, they'll just be proving a point I already concede. Now, this is all important because he mentions two things that are, again, fallacies. So most nodes may be run by specialists, meaning that nodes are not meant to be run by every person in their basement. Okay. And then secondly, he says that the security of the network grows as the size of the network and the amount of value that needs to be protected grows. This is also important because this is going to help us understand why the network structure emerges the way it does. Now, he then talks about that it's vulnerable at the beginning when it's small. So this actually explains why the BTC network has a 1 megabyte cap on the size of blocks. And this is precisely because through convincing done by Hal Finney and Ray Dillinger, they convinced Satoshi that Bitcoin was vulnerable to DDoS attacks while it was young and not valuable. So Satoshi reluctantly agrees and then describes exactly how you could phase in a block size increase, saying that it can be in versions way ahead so that by the time it's needed, it'll be there. Of course, it was needed in December of 2017, and it wasn't there. Now, last thing I want to talk about is, again, this idea that everyone needs to run a node. Satoshi addressed this precisely. The current system where every user is a network node is not the intended configuration for large scale. That would be like every Usenet user runs their own NNTP server. The design supports letting users just be users. The more burden it is to run a node, the fewer nodes there will be. Those few nodes will be big server farms. The rest will be client nodes that only do transactions and don't generate. He then, this post is remarkable because he then describes why zero confirmation transactions work. But we're not even going to touch on that today. So all of this is important because what we're really doing here is trying to help people understand that the myth of the network structure is just that. It's a myth. So Bitcoin is not a mesh network. Bitcoin actually is a different network altogether. Because it is a Stackelberg competition, because the actors are so fiercely in competition with each other, they are incentivized to be directly connected to one another, and they form what's called a small world network. Okay? So you've heard us talk about this 8,000 times probably, but we're going to touch on it again. So what is a small world network? It was first coined by Stanley Milgram. And this article, again, I encourage everyone to read this, is based on a book called Complex Social Networks, which very dense book. I encourage everyone to read it if you have the capacity to. So Stanley Milgram coined the term, and it describes a situation where despite facing a very large population, an individual can typically succeed in contacting any other in the population through a short path of intermediaries. So Milgram did some experiments with trying to get people to send a letter from Nebraska to Boston, and he found that on average it took less than 6 hops before before the letter would be delivered. Now this is very important. When Milgram's experiment was trying to be validated, they found something. The key point. So upon validation of Milgram's experiment, researchers identified the importance of individual incentives besides searchability as a primary factor in chain completion, i.e. reaching its final destination. And pretty much they confirmed Milgram's results, but that's important. Incentives plays a very large role in determining the structure of a network and the network distance. So if you're having a hard time understanding what a small world network is, we can talk about this really briefly. Again, we talk about this a lot, so there's plenty of times where we've talked about it. It can point you in other directions, but this is a traditional lattice network or a mesh network. I'll show you another mesh network down here to get you helping to understand. So if I were to pull up this here, you can see that a mesh network suffers from the problems of having to hop across many nodes to get from destination to destination. So in the case of trying to get from here to here in the node, in the network, from one side to the other, we might have to bounce around maybe, since the Lightning Network here was so small at the time, you probably could do it in 6 hops. But actually the network distance in Bitcoin is something like 1.3. That is the average network distance in Bitcoin, which means that that's the average amount of hops it takes to get one transaction to a node that is connected to the rest of the network. So this is very important because actually the academic definition of a decentralized network is specifically how many edges there are connecting one node to another node. And what you're going to see here is that a small world network fits that description very well. So we're going to carry on. So again, mesh network, lattice network, this is very similar. So if I want to get from number 10 up here to number 0 down here, I have to go 1, 2, 3, 4, all of these different hops. Now, what if I could find a path that got me maybe to 15, which was directly connected to 0, right? So that would be just 2 hops to get to 0. So a small world network is actually a very, very simple concept where you can think of this variable P, and you take a regular lattice network and you increase randomness. So as you go from 0 to 1, you slowly become more densely connected. And this is important because even if we just increase P by a little bit, you can actually already see that the ability to get from one node to another quickly increases. So if I want to go from here to here, for example, I can actually go, here, there. I can go here, 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 maybe here, and then here, right? There's a lot of possibilities. So as P increases more and more, the ability to get from one node to another increases. Now, inside of Bitcoin, this is really important because there's an incentive to be densely connected to the rest of the network for a few reasons. And this is actually addressed in the steps to running the network. So new transactions are broadcast to all nodes. So this is the step to run the network. This is very important because this basically means that you are always connected to all the other nodes in the network, constantly broadcasting transactions. You want to pick up every transaction because there's a fee associated with every transaction. So there's an added incentive to pick up the transaction fees alone. However, there's a much bigger added incentive. As you remember from the proof of work section, that a block is built on top of by other nodes in the network, but only if a block is built on top of does a miner get the block reward associated with finding that block. So, and you can see here when a node finds a proof of work, it broadcasts the block to all nodes. They express their acceptance of the block. So you are directly incentivized to be directly connected to the rest of the network precisely because you want your block to be built on by other people so that you get the block reward. So the incentives are already playing out. There's an entire section about incentives here. You can read that. It talks about that as well. But basically, this comes back to the idea that when validating Milgram's experiment, incentives are a key part to decreasing the network distance in the network. You can see here we have this random network when P goes to 1. But remember, in Bitcoin, why am I going to forget the network connections that I already have? So this is actually going to be a complete ring with all these densely connected links in the middle. So there's actually a paper that's been done that actually shows that network distance in Bitcoin is actually close to 1.3. That is unprecedented in any modern network known. So this is extremely important. What we're talking about here is an entirely different network from the internet. And so this is important because if you're going to say that Bitcoin shouldn't be used as a network to store data, for example, but instead think that something like IPFS should be used, or any other flavor of these quote unquote decentralized systems, you actually introduce yourself to a very vulnerable attack. And that is noted in this paper called On Bitcoin and Red Balloons. So this paper actually doesn't, I mean, it talks about Bitcoin, but it's a very important paper because it talks about how to Sybil attack a network and how you can create a network with the correct incentives that is Sybil proof. And they conclude that any network with 3 or more hops is vulnerable to a Sybil attack. As I told you, Bitcoin is 1.3. Okay. And of course, when I talk about the Bitcoin network, I only mean the miners in the network, because they're the only ones that actually build on top of blocks. They're the only ones that actually can change the rules. They're the only ones that can double spend. They are the network. Okay. So Bitcoin is actually the first Sybil proof network that I know of. This paper done by some Microsoft researchers, it talks about a 2009 DARPA network challenge, finding red balloons. And it talks about, again, the incentives associated with creating that small world network. So I'm going to come down here just a little bit because there's a few things that are important to understand. So the Bitcoin network has 3 key characteristics that make it an entirely different network capable of study, and an entirely different network that is capable of more than what we're aware of in modern networks. So these reinventions of other altcoins and cryptocurrencies and decentralized solutions are actually sacrificing these 3 characteristics to get what they want, whereas it's built into Bitcoin. So this first one is robustness. So robustness of a network is actually the resilience of it to being taken down, essentially. In Bitcoin, the nice thing is that it is distributed. And so if one miner is taken down, the network functions the same. So it's actually decentralized and distributed in the fact that there's always going to be more than one actor. There's always going to be competing factions, and therefore it's robust from being taken down. In fact, the Bitcoin network has never been taken down in its entire history. Search. So search is the procedure by which individual nodes may look for, access, and disperse information. This is actually important because a small world network has high characteristics of searchability, which is actually preferable if you're trying to have a network that is a better BitTorrent, for example. So BitTorrent is a file sharing network. But the problem is that it's very hard. It's not a very searchable network. And what I mean by that is that if one person in New Zealand has a file that I want here in America, I have to hope that I can get directly connected to that node in New Zealand. So I have to find that node in the network. And unless that node is densely connected, it's very unlikely I'm going to find it. So in Bitcoin, we actually had the benefit of being densely connected, and searchability is high. And so this is going to be important as Bitcoin grows to encompass the internet. Diffusion, this last piece here, is the multifaceted phenomenon that governs the gradual spread over time of any kind of signals. This is also important because really all networks in diffusion you can think of as like viruses. So how do viruses spread in the human network? And there's actually a lot of analogies to the way Bitcoin actually functions very, very similar to a biological network. And we talk about that a lot in this piece. But biological characteristics of social networks is actually they appear a lot in social networks. I don't think there's too much else here I need to go over. There's a lot in here that I could talk about all day pretty much, but we can just touch on decentralization, because what Bitcoin actually enables is the ability for peers to interact with other peers through the use of the network. So the nice thing about Bitcoin is that, and I give a little thought scenario here, as to what is actually more decentralized, a network where people are all running nodes, or a densely connected network where I can go from one person to another in the smallest amount of hops possible. And really, because Bitcoin has the actual characteristics of decentralization, which is they have a high edge count for nodes, we actually end up with a more decentralized network than anything we've ever seen before. So that's all I'm gonna talk about there. I'm really coming to a close here because there's a few things that I want to just drive home. Is that, again, Bitcoin is capable of scale. So all these things I just talked about, these things actually, the security of the network grows as the size of the network and the amount of value that needs to be protected grows. So everyone is asking, well, what can I do for Bitcoin SV, which is, of course, the only Bitcoin that I've been describing here. And that is make Bitcoin SV as valuable as possible. And that naturally grows the security of the network, and it grows the network itself. So this is all that's important. And again, nodes may be run by specialists. He says at the time with multiple GPU cards. He then goes on to say it'll be run by server farms. But again, there's no scaling problem here. So Bitcoin actually is capable of all of this scale that we're talking about. And one very important thing as well, that the fees should not be artificially planned. This transition to fees is not controlled by some human in charge of the system, though, just individuals reacting on their own to market forces. So that does not describe the other two variations of Bitcoin. Pretty much all I have. I've given you probably a lot that to look into if you want. Very, very simple concepts, very, very simple understanding, but these things are important, and they're going to be important as we continue to talk about what Bitcoin is capable of. The last thing I'm going to say is that Bitcoin solves the double spending problem. It solves what is called the Byzantine generals problem. And I will go ahead and pull that up real quick. Well, there's a lot I could show you. I mean, what is I don't know how good this is, but the Byzantine generals problem. So Bitcoin is cited as a solution to this problem. You can look up exactly what it is, but it's basically the idea that it's a game theoretical problem that was previously thought unsolvable. Or how do you get generals to act the same way if they can't reliably be communicating with each other? And Bitcoin solves that through incentives. It solves that through economics and through the natural game theory that arrives from nodes competing with each other. The important thing to understand, again, Bitcoin didn't introduce blockchain to the world. It introduced the use of economics to prevent the double spending, to solve the double spending problem. And really, that double spending problem is itself part of the Byzantine generals problem. So economics is a key part of this. I'm done. I really have nothing else to tell you. This is just a crash course, short video that you can send to people, help them understand. And that's all I have. So thank you.